I want to ask you something, and I want you to actually try this. Not just listen, but genuinely attempt it. I want you to imagine nothing. Not darkness, not empty space, not a quiet room with the lights off. Nothing. No space. No time. No matter. No energy. No darkness, because darkness needs space to exist in. No silence, because silence needs time to exist in. Just nothing. Absolute, complete, total nothing. Try it. Really try. You can't do it, can you? Every time you get close, your mind fills the void with something. A dark background, a sense of space, some kind of backdrop for the nothingness to exist against. And here's what I find fascinating about that. It might not just be a failure of imagination, it might be your mind, without knowing it, correctly reflecting something true about the universe. Because physics has discovered something extraordinary. True nothing, absolute, complete, total nothing may be impossible, not rare, not hard to achieve. Impossible. The universe, it turns out, cannot be empty. Not even in principle, and understanding why that's true will change the way you think about existence itself. My name is Dr. James Mitchell, and this is Science Explained Properly. Let's begin. Let's start with the most common version of nothing. Empty space, a vacuum, a region where everything, all the air, all the matter, all the particles, has been completely removed. The kind of nothing you'd find in deep space, far from any star or planet. For most of human history, that's what nothing was assumed to be. A void, a passive, featureless backdrop against which the universe did its thing. Even the ancient Greeks argued about it. Aristotle famously insisted that a true vacuum was impossible, that nature would always find a way to fill any void. Most people dismissed him. Here's the thing. He was right, just not for any reason he could have imagined. Because when physicists in the 20th century began examining what we call empty space, really examining it with the full power of quantum mechanics, what they found stopped them in their tracks. Empty space is not empty, not even slightly. It is a restless, fizzing, endlessly active place, constantly doing something, even when there's nothing in it. And to understand why, we need to talk about one of the most important ideas, and most misunderstood ideas, in all of physics. In the 1920s, a German physicist named Werner Heisenberg discovered something that seems, on the surface, almost too strange to be true. There are certain pairs of properties in nature that cannot both be precisely known at the same time. Not because our instruments aren't good enough, not because we're not looking carefully enough, but because nature itself doesn't allow it. The most famous example is position and speed. The more precisely you know exactly where a particle is, the less precisely you can know how fast it's moving. And the more precisely you know its speed, the less precisely you can know where it is. It's not a measurement problem. It's a feature of reality. Now, I want you to hold that idea. Nature sometimes refuses to be perfectly precise, because we're going to need it in a moment. There's another pair of properties that works the same way: energy and time. The more precisely you pin down a specific moment in time, the less precisely energy is defined at that moment. Here's why that matters. Imagine you're trying to take a photograph of a sprinter. If your shutter speed is very fast, 1,000th of a second, you get a sharp, precise image. You know exactly where the sprinter is at that precise moment, but you've lost all sense of motion. The image is frozen, still. Now slow the shutter speed right down. the sprinter blurs across the frame. You've captured motion, energy, movement, but you've lost the precise moment. You can't have both perfectly sharp location and perfectly captured motion at the same time. Nature works that way. And for energy and time, the consequence is this. In any given moment, in any given region of space, the energy can never be precisely zero, because zero is a perfectly precise value. And nature doesn't allow perfect precision, so energy fluctuates. Always, everywhere, even in the emptiest region of space you can imagine. Does this make sense so far? I hope so. Because here's where it gets interesting. Think of empty space like the surface of the ocean on a perfectly calm day. From a distance, from an aeroplane, say, it looks completely flat. Still, featureless, empty. But get close enough and you see something different. Ripples, tiny waves, constant microscopic movement. The surface is never truly still. Even on the calmest day, even in the most sheltered harbour, the water is always moving at some level. Empty space is exactly like that. From a distance, from our everyday human perspective, it looks like nothing. Flat, still, empty. But at the quantum level, at scales far smaller than an atom, it's in constant motion, rippling with energy, never still, never truly empty. Physicists call this the quantum vacuum, and it's not just a theoretical idea, it has real, measurable physical effects on the world around us. Let me show you what I mean. In 1948, a Dutch physicist named Hendrik Casimir made a remarkable prediction. He said, "Take two perfectly smooth metal plates. Place them in a complete vacuum, all the air removed, all the particles gone. Put them incredibly close together, just a few nanometers apart." According to classical physics, the physics of Newton and everyday experience, nothing should happen. There's nothing between the plates, no air to push them, no particles to bounce between them, no forces to act on them. They should just sit there. But Casimir predicted they would be pushed together. By nothing. Here's why. Remember those energy fluctuations we talked about? The constant rippling of empty space. Those fluctuations manifest as something physicists call virtual particles. Pairs of particles that pop into existence from the energy of empty space exist for an incredibly brief moment and then annihilate each other and disappear. This is happening everywhere, all the time. In the space between your hands right now, in the air in front of your face, in the emptiest regions of deep space. The vacuum is constantly, briefly, creating and destroying particles. Now, back to those two metal plates. Virtual particles are appearing and disappearing both between the plates and outside them. But the gap between the plates is so tiny that only certain sizes of virtual particles can fit in there. Outside the plates, all sizes are possible, so there are more virtual particles pushing in from outside than from between. And the result? The plates are pushed together. By the energy of empty space. By nothing. This was tested in a laboratory in 1997. The force was measured precisely. It matched Casimir's prediction exactly. Empty space pushes back. The nothing between those plates is not nothing at all. Now, I want to pause here for a moment, because I know this sounds like I'm asking you to accept something quite extraordinary. Particles appearing from nowhere, empty space with energy, nothing that pushes. It sounds like science fiction, but the Casimir effect is as well established as gravity. It's been measured dozens of times in laboratories around the world. It's real, and it tells us something profound. The vacuum, the emptiest thing we can create, is one of the most active places in the universe. Now let's take this one step further, because virtual particles are just the most visible symptom of something deeper. Quantum field theory, the most precise and accurate scientific theory ever developed, tells us that every type of particle in existence corresponds to a field that exists everywhere in space simultaneously. There is an electron field permeating all of space, a photon field, a quark field. These fields are everywhere, all the time. They cannot be turned off, they cannot be removed. Even in a perfect vacuum, even if you somehow stripped away every particle, every photon, every trace of matter, these fields would still be there, still fluctuating, still containing energy. Physicists call this the zero-point energy of the vacuum, the energy that remains when absolutely everything else has been taken away. The energy of nothing. And here's something that will connect this back to something we've discussed before. Remember dark energy, that mysterious force accelerating the expansion of the universe that we touched on in our structure lecture. Many physicists believe dark energy is connected to this zero-point energy of the vacuum, that the force driving the universe apart, the force that will ultimately determine the fate of everything, may be the energy of empty space itself. Nothing, as it turns out, might be responsible for the ultimate destiny of the cosmos. Stay with me here, because now we arrive at the deepest question of all. We've established that empty space isn't empty, that the quantum vacuum fizzes with energy and virtual particles, that nothing in the everyday sense doesn't really exist. But this raises a question that has haunted philosophers and scientists for centuries. If nothing is impossible, if the universe refuses to permit a true void, why does the universe exist at all? Why is there something rather than nothing? Let me put that another way. If the quantum vacuum always contains energy, always fluctuates, always produces particles, where did the quantum vacuum come from? And here's where I want to be very honest with you, because this is the point where physics reaches its current frontier. Some physicists, including the late Stephen Hawking, proposed that the universe itself arose as a kind of quantum fluctuation. He proposed that, from some primordial state, a fluctuation occurred that gave rise to space, time, matter, energy. Well, gave rise to everything. It's a remarkable idea, and it's mathematically serious. But it comes with an immediate problem. A quantum fluctuation requires a quantum vacuum to fluctuate in. And a quantum vacuum, as we've seen, is not nothing. It has energy, it has fields, it operates according to the laws of quantum mechanics. So saying the universe came from a quantum vacuum doesn't fully answer the question. It just moves it back a step. Where did the quantum vacuum come from? Where did the laws of physics themselves come from? Why does anything, any rules, any fields, any energy, why does any of it exist rather than absolute nothing? And the honest answer is, we don't know. We have pushed our understanding to the very edge of existence, and at that edge, we find a question we cannot yet answer. I think it's important to say that plainly, not to fill that gap with false certainty, but to sit with it honestly, because that open question, that genuine, unresolved mystery at the heart of existence, is not a weakness of science. It is science doing exactly what it should do, pushing to the boundary, naming what it finds there, and being honest about what lies beyond. Here's something worth considering before we close. The fact that nothing seems to be impossible, that the universe appears to refuse a true void, tells us something beautiful about the nature of reality. The universe does not default to emptiness. It defaults to existence. Left to its own devices, governed only by the laws of quantum mechanics, space fills itself. Fields fluctuate, particles appear, energy flows. Existence seems to be, in some deep sense, the natural state of things. We spend a lot of time wondering why the universe exists, framing the question as though nothing is the expected baseline and something is the surprise. But physics suggests it might be the other way around. Nothing is the anomaly. Something is what happens when you let reality run. And if that's true, if existence is in some sense the natural state of things, then the question shifts. Not why is there something, but why would there ever have been nothing? Let's bring this together. We started with a word, nothing, and we tried, genuinely tried, to imagine it, and we couldn't. We found out today that this might not be a coincidence. Empty space is not empty. It fizzes with quantum fluctuations, with virtual particles appearing and disappearing, with zero-point energy that cannot be removed. It pushes back, measurably, reproducibly, in laboratories around the world. The vacuum is alive. And the deeper we look, the more it seems that existence, something rather than nothing, may be the most natural state of all. Now here's what I want you to sit with. Every atom in your body, every particle of matter you're made of, is an excitation of a quantum field that permeates all of space. You are not a separate thing moving through an empty universe. You are part of the same fabric as the vacuum itself. The same fields that fill empty space also fill you. The boundary between you and the universe around you is less clear than it appears. You are the universe. Briefly, improbably, beautifully organized into a form that can look back at itself and ask questions. Why does anything exist? Why is there something rather than nothing? Physics takes us to the very edge of those questions. It shows us that nothing is unstable, that the vacuum is alive, that existence seems to be what reality does when left to itself. But the final answer, the deepest why, remains open. And maybe that's exactly as it should be, because a universe with no remaining mysteries would be a smaller, less interesting universe than the one we actually live in. The questions that sit just beyond our reach are not gaps to be embarrassed about. They are the most honest thing we have. Evidence that reality is deeper and stranger than we have yet managed to understand. And you, right now in this brief, luminous moment of existence, are part of that strangeness. Not watching it from a distance, part of it, made of it. In the next lecture, we'll turn to one of the most fundamental and most misunderstood concepts in all of science. Something that powers every star, every life, every thought. What energy actually is. Now, I did promise at the end of our last lecture that this video would be about energy, and I apologize for that. But I hope you'll agree that this detour was worth it. After all, I really wanted to talk about, well, nothing. Thank you for listening. I'll see you in the next lecture.